Jai Hind, dear students. I'm Dr. Preeti Mittal. The chapter that we are going to start today is sound. We hear different sounds in our life, but have you ever wondered at how these sounds are produced? These sounds are produced because of the vibration of the particles. So when I'm speaking, at that time also, the cartilages present in my vocal cord are vibrating, and that only produces the sound. So if we talk about the sound, have you ever seen these vibrations? Because I can't see my vocal cord. So have you ever seen these vibrations in any of the things that is producing the sound? Yes, you all have seen that. Just recall that when you went for some party and when some loud music was playing, then you can see the movement of the drum of the speakers. Loudspeakers drum is there and that is continuously vibrating. And that's vibrations you can even see because that is very loud music. So you can even see those vibrations. So when it is vibrating, how this sound is propagating? Let's talk about it. Sound waves are mechanical waves. Mechanical waves are those waves which need a medium to travel. So when the sound is traveling, that requires a medium. That is different from light because light doesn't require any medium. It can travel even in vacuum. But sound always requires some medium and it cannot travel in vacuum. That is why we get the light from the sun, but we can't hear the sounds going on in the space. So let's see what is happening when the sound waves are moving, when it's propagating from one place to another, how this propagation is going on. So just suppose we have some particles in the medium. Okay, there are many particles in the air. So suppose the sound is going to propagate through air and these are the particles that are present in the air. And this is the drum of your loudspeaker. Now, when it vibrates, when it comes out, it will come out first and then it will move in. This is the vibration of the drum. So it will once move out and then move in. So when it will move out, it will push these particles in the forward direction. So these particles will be pushed forward and so in a region next to it, there will be area where the number of particles will be moved. So now they were pushed from here and so what will be there? Then the particles in the next area where they will be pushed, that number of particles in that area will be increased. But after pushing it, the drum went back to its original position. It went back there. And so what happened? The particles were all moved there. So in this area, from where it was pushed, in this area, the number of particles will be very, very less. Okay, so where they will be pushed at that particular area, the number of particles will be more, and from where that was pushed, the number of particles in that area will be less. So what happens? There is alternate production of areas of more particles and less number of particles. Alternately, we will see that in the air, in the medium, whatever could be the medium, so the number of particles will be constantly, like one area will be having more number of particles and the next consecutive area will be having less number of particles. So we'll have this kind of a pattern that will be shown by the number of particles. Now the area which is having more number of particles, this area is known as the area of compression. This is the area of compression. And from where the particles have been moved out, this area is known, where the particles are less, this area is known as rarefaction. Compression and rarefaction. So now what will be happening? Since in this area, the number of particles is more, so the density of particles is more. And when the density of particles is more, there is high pressure in this area. So in the area of compression, there will be high density or high pressure. High density as well as high pressure. Why it is high pressure? Because the particles are very much closely packed in that area. So there are a lot of particles in this area. So this area will be having a high pressure and more number of particles are there. So we call it as high density also. But in the area of rarefaction, what will be there? There will be low density because the number of particles is less, and low pressure also because the number of particles is less, so there is not much pressure in that area. So this is the area of low pressure. Now if we plot this as a graph, that the area, how much pressure is there, so we plot this pressure or density as a graph and we take this as a mean position. Mean position means where the pressure is neutral. When the sound is not there, whatever is the pressure, that pressure is taken as a baseline and we plot the graph for the pressure. Then what kind of a graph will be there? There are areas of high pressure and there are areas of low pressure. Then again high pressure and areas of low pressure will be there. This point will be representing the pressure high and this point is representing when the pressure is the minimum or lowest, because this is the pressure area what we are representing. And this mean position, mean line here represents the neutral pressure. When there was no sound propagating in the medium, whatever was the pressure of the particles there, that is shown by this mean position line. Okay, so the area of high pressure is represented here, and when the pressure is going to fall down, this is the area of low pressure. This high pressure area is known as crest. When the pressure is maximum at a point, that point where the pressure is maximum, that point of the graph is known as crest. And when the pressure is lowest, that part is known as trough. So the point where there is high pressure and the pressure is maximum, that is crest, and the lowest pressure area is known as trough in our graph. Okay. Now I told you that sound waves are mechanical waves. So what other kind of waves are there? That also we need to learn. That is transverse waves. Okay. Now we'll see the difference between transverse waves and mechanical waves. First talk about mechanical waves. The sound waves are mechanical waves. So in this waves, you can see that the particles are being pushed forward, and once they are pushed forwards, they will eventually come to their own position also. So the particles will be vibrating in a direction parallel to the propagation of sound. The sound is propagating in this direction, suppose, and the particles are also vibrating to and fro. These particles never go from the area where the sound is produced to the area where the sound is being heard. They just transfer the energy from one particle to another. Okay, so suppose if the first particle was getting the energy, that energy will be given to the second particle, then the second particle will be giving the energy to the third particle. In that way, the particles will be passing this energy from one particle to another. The first particle is not going to take the sound wave right up to your ears. Okay, so such waves, when the particles are transferring the energy from one particle to another, so such waves are known as longitudinal waves. Okay, such waves are known as longitudinal waves. Fine. So it requires a medium. So it is a that requires a medium. Sound requires a medium. So it is known as a which kind of a wave? That is known as a mechanical wave. But since the particles are moving in the direction of propagation of sound waves only, so such waves are known as longitudinal waves. Okay, it's just like passing the parcel. The energy is transferred from one particle to another. Okay, you must have played passing a parcel, no? So it's similar to that. Now we'll talk about transverse waves. The light waves are transverse waves. What are transverse waves? Suppose if some form of energy is traveling in this direction and the particles are moving just up and down. They are just moving up and down, perpendicular to the direction of motion of the wave. So if a wave is traveling in the forward direction and the particles are just vibrating up and down, that is perpendicular to the direction of propagation of wave, such waves are known as transverse waves. Okay, for example, if you throw a stone in water, then what will happen? The water is going to move up and down. So that up and down movement that is perpendicular to the direction of propagation of wave is known as transverse waves. Light waves are also transverse waves. But remember, light doesn't require any medium. So it is not the particles which are moving up and down in case of light. There are some energy particles, energy photons are there that are traveling up and down. Okay, that you will read in your higher classes. So just remember two things from here. Sound waves are mechanical waves, that is require medium. Sound waves are longitudinal waves, that is the particles are oscillating to and fro, and the direction of oscillation is same as the direction of motion of the sound wave. Okay, now I told you that the sound, when the sound is traveling, only the energy is transferred from one particle to another. Okay, these particles in the medium are not going from one place to another. It is only the energy that is being transferred from one place to another. Remember that. Okay, now we will see about some of the characteristics, features of sound waves. So I'm just going to erase this off. I hope this is clear, but we'll let our diagram be there only, the graph that we have plotted. So one thing that's very important we have seen is the area of compression is the area of high pressure, and the area of rarefaction is the area of low pressure. So if we plot a graph, then based on this graph, we can learn many things. So just we will learn about some of the terminology related to sound waves. These terminologies can come as 1 mark questions for your in your exams as short note as well. Okay. So the first thing is frequency. Frequency describes the number of oscillations per unit time. Means in 1 second, how many sound waves are there? How many compressions and rarefaction? One compression and one rarefaction will make one complete wave. So this is one compression and this is one rarefaction. This complete will be one wave. This complete area which covers one compression and one rarefaction, that is known as complete one wave. So how many waves are there in 1 second? That will give you the frequency. Okay. So the number of waves that are there in 1 second, that is known as frequency. Fine. So that will include, one wave will include one compression and one rarefaction. Fine. Now, pitch of a sound is there. You must have heard that females have a high pitch, male voices a low pitch sound. So this pitch defines the frequency. If I talk about two waves, I'll just draw one more here. Okay. So suppose this is also in 1 second and these number of waves are also there in 1 second only. So in 1 second, how many waves were there in that figure? That was just having two waves. So it was a low frequency sound. But here the number of waves is high. So it is a high frequency sound. So the number of waves that occur in 1 second is known as frequency, and the pitch is also dependent on frequency only. If the number of frequency is high, then it is called a high pitch sound, and if frequency is less, then it is called a low pitch sound. Some examples of pitch doesn't has to do anything with the loudness. Okay, loudness is something different. We'll talk about it. But if we talk about some examples of high pitch sound, for example, a female voice is a high pitch sound. Apart from that, the buzzing of a bee, that is also a high pitch sound. But a lion roar is a low pitch sound. Okay, and apart from that, male voice is also a low pitch sound. Okay, so pitch of a sound is depending only on frequency and it has nothing to do with the loudness. So on what factor loudness is going to depend, we'll see that. But before that also, in frequency only, learn these points also. In your book, there it is given very at different places. We'll just compile all the topics related to one particular topic at one place only. That will make your learning easier. So what is tone? Tone is a single frequency. So if you hear a voice like this, beep, so it is having a single frequency. The frequency is not changing. So such a voice is known as tone. Okay. And what is a note? When there is a mixture of different frequencies, such a sound is known as a note. So when different frequencies are there, changing frequency is there, then it is known as note. And when it's a single frequency only, then it is known as a tone. Now, if it asks in an exam, how will you remember that, all that? Just remember by one example, just to memorize the thing. Note, when you write the notes, they're always different. Now, sometimes you're writing SST, sometimes Hindi, sometimes in Sanskrit, sometimes in science. So when you're preparing your notes for different subjects, for different topics, they're always different. So note is different frequency. And tone, word only, like sometimes your mother asks you, change your tone. Don't talk to me in this tone. So you don't like a single frequency, single mood. So you are asked to change your tone. Okay. So by that way, you can remember what is tone and always writing the notes, these pretty students. So what that is, note is different frequencies. Okay. Now we talk about time period. Time period is the time taken to complete one complete oscillation. For complete one wave, whatever is the time taken, that is known as time period. So time taken to complete one compression and one rarefaction, that will be known as time period. Now you can easily think that if in 1 second two waves were there and I called it as the frequency is 2. So what will be the time taken for one wave? It will be half a second. Okay. So frequency and time period are inversely proportional to each other, and frequency is 1 upon time period. So here my frequency was 2. So what will be the time taken for one complete wave? So we can write the reverse also. Time period is equals to 1 upon frequency. So 1 upon frequency means time period here will be half. Okay, in half second one wave will be completed. The frequency of sound is not so low, but I'm just telling this example to make your things easier. Okay, so frequency and time period are inverse of each other. Okay, higher the frequency, less time will be taken for a particular wave. Here the frequency is high, so each wave will be taking a very less time. Okay, so that is time period, time completed for one complete compression and rarefaction. That is known as time period. Now we will talk about amplitude. We will talk about amplitude because we were worried about the loudness. That I told you that loudness is not dependent on frequency. Then what is loudness? So this maximum pressure changes that are occurring in a wave, this distance from the base position, how much the pressure is changing, that defines the amplitude of the sound. So if the sound waves, suppose I plot another graph and here this is there. The frequency is remaining the same, but the pressure changes are more. The compression and rarefaction is more. Then this dotted line is representing higher amplitude. Okay, so the force with which we are pushing the waves, that will decide the amplitude. If I try to speak louder, then I will be applying more force, and I will be pushing my cartilages on the vocal cord more. So that will be producing a higher amplitude. So the distance between, if the crest and the mean position is more, that means it is a louder sound. Okay, so that is going to define our loudness of a sound. That will be dependent on the amplitude. So the maximum pressure changes that are occurring in a sound wave, that will help you to know its amplitude. Okay. Next comes the intensity of sound. Now this intensity of sound is the amount of sound energy that is transferred, per unit area in a unit time. Okay, the amount of sound energy that is transferred per unit time means in 1 second, what is the amount of energy transferred per unit area? Means the area is 1 meter square, then that is known as intensity. Okay, the amount of sound energy that is transferred per unit time in 1 second, or you can say in 1 second per unit area, that is known as intensity. Now this intensity of sound could be measured, but this loudness and intensity are not the same, because loudness will depend from person to person. Just imagine an old person, they usually like to hear the sounds at a higher loudness. That sound is okay for them, but maybe very loud for you. When your grandmother watches the TV, you must have observed sometimes, and when she's watching, that depends on the perseverance of the power of the ears, how much they can collect the sound waves. So loudness, that depends from person to person. A voice that is loud for you may not be loud for someone else. Okay, so but intensity is a measurable quantity. You can measure that, and it doesn't vary from person to person. It is the energy transferred in 1 second per unit area. Okay, I hope that is clear to you all. Next comes the wavelength. Wave ki length. It's very easy. So the length of one particular wave, that is the length of one compression and one rarefaction, that is known as wavelength. And this wavelength is represented by the symbol. This is the length of one particular wave, and this wavelength is represented by the symbol lambda. Okay, so this is a symbol, and that is representing wavelength, and its symbol is lambda. Okay, since its length, its unit will be meters. The SI unit of wavelength will be meters. I just forgot to tell you the SI unit of frequency, that is hertz. Frequency is always measured in hertz, H-E-R-T-Z. It's measured in hertz. Time period is measured in seconds because it's time, so SI unit of time is seconds only. Okay. Now we talk about quality or timbre of sound. Quality or timbre of sound is like if two persons are there speaking with the same loudness and same frequency also, then also the quality of their sound is different. For example, quality of sound of Lata Mangeshkar is different from that of Asha Bhosle and very different from that of mine. So that quality or timbre of the sound depends from person to person. That doesn't depend on the frequency. Two sounds could be having same frequency, same loudness, but still the quality of the sound is different. That is, the timbre of the sound is different. And next we are going to do some numericals, but before that we'll learn about the speed of sound. Now, when the sound wave is traveling, the distance covered by the sound wave per unit time is known as its speed. Okay, so you always know what is the formula of speed. You always knew that for whenever we are talking about speed in general, we talk that speed is distance upon time. So when we talk about sound wave, what is this distance? This is the wavelength. The distance covered between one consecutive compression and rarefaction, that is wavelength. And so here when we talk about the speed of sound, it could be given by wavelength divided by time. Now divided by time is equal to 1 upon time period is frequency. So wavelength multiplied by frequency will give you the speed of sound. Wavelength multiplied by frequency of the sound wave will give you the speed of that sound wave. Now the speed of the sound wave doesn't at all depends on whether you are speaking loud or slowly. Even if I speak softer or louder, the speed is not going to depend on that. This speed of the sound depends on two things. Speed of the sound depends on the medium and the temperature. These two things are going to decide the speed of sound. So speed of sound is going to be different for different medium and for different temperatures also. How they are dependent? Speed of sound is maximum in solids and minimum in gases. Okay, so if you want to check that, just if you just put your ears to a railway track. So before you hear the sound of a train coming through the air, before that only you can hear that sound if you put your ears next to a railway track. So the sound travels faster in solid because the particles are very close to each other. So energy is transferred very easily in them. Okay, so the speed of the sound is maximum in solids and minimum in air, minimum in gases. Okay, remember that, very important. Fine, but don't do that experiment ever, and it's very dangerous to do that. Now next thing is temperature. Higher the temperature, more will be the speed of sound because it's the energy. So when the particles are already having more energy at high temperature, the particles will be having higher energy. So it's easier for the energy to be transferred. So higher the temperature, more will be the speed of sound. High energy, more speed. Solids, more speed. Remember that. Okay. Now, based on this, we are going to practice just two numericals that are given in your NCERT book only, and we'll just practice them. Okay. So I'll read the question for you and just try to do it by yourself. So just let's see how many of you are able to get the correct answer. Just let me know in the comment section. If you were able to do the question by yourself, just give a thumbs up. One question that I'm reading, that is, calculate the wavelength of a sound wave whose frequency is 220 Hz. Now, the symbol for frequency is nu. This is the symbol used for frequency, but I try to avoid that because the symbol used for speed is V, and they look quite similar to each other only. Okay, so it's better to just write the word frequency and write the word speed. Or for speed, you can just use the symbol, so it's clear that for frequency, you are using the word frequency. Okay, frequency is given 220 Hz, and the speed is 440 meter per second. You have to calculate the wavelength. It's very easy. You have to calculate the wavelength. So just putting the values in the formula, speed is 440 is equals to wavelength. You have to find out frequency is given 220 Hz. So wavelength is equals to 440 divided by 220, and that will make it 2 meters. The wavelength will come out to be 2 meters. Very simple question. Let's do the next question. A person is listening to a tone. Tone means single frequency. Frequency is 500 Hz. Sitting at a distance of 450 meters from the source of sound. What is the time interval between the successive compression from the source? So you know that time period is 1 upon frequency, that is equal to 1 upon 500, and that will make it 0.002 seconds. So this 450 meters distance is just given to confuse you. They're just asking you time period, and you know that frequency and time period are inversely proportional to each other. So time period is 1 upon frequency, and that will give you the answer. Fine, everyone? Now, the topic that we are going to start with is reflection of sound. Whenever you have visited any hilly areas, especially at a great height surrounded by mountains, you must have tried one thing, that there is a echo point. Means from where you can shout something and you can hear your voice back. So if you shout science, then you will hear science, science, science multiple times. So that is the phenomenon responsible for that is reflection of sound. Sound waves gets reflected back after striking different objects, and this reflection of sound waves follows the laws of reflection of sound, that is quite similar. It's exactly actually the same as you have read about reflection of light in class 8. So what are the laws of reflection of sound? The angle of incidence is equal to angle of reflection. So whatever is a sound wave, if it is striking an object, and this is the normal drawn to that object, that is a 90-degree at that particular object, then the reflected ray will be having the same angle as the angle made by the incident ray of sound. Second point of law of reflection of sound is the incident ray, the reflected ray, and the normal, they all lie in the same plane. So these laws are same as that of the laws of reflection of light. Next, a very beautiful phenomenon related to sound is reflection of sound that we can hear as distinguishing from each other. That is echo. Echo is when you call out something and you are able to hear your words back again. That is echo. Why this echo occurs at hilly areas or when you are surrounded by mountains? What is that echo point? When there are certain things which are at great distance from you, so that the sound waves can get stuck with them and get reflected back to your ears, so that you can hear able to hear that. That is known as echo. For an echo to occur, you must be at an open space only. You can't hear echo at a closed space, because that distance required, minimum distance that is required for echo, that is a large distance. Why that minimum distance is required? The human eye, the human ear, sorry, the human ear can hear two sounds distinguishedly if if the time between the two sounds is at least 0.1 seconds. So the time interval between two sounds needs to be at least 0.1 second. Then only our brain will be able to interpret two different sound waves. Now, in case of echo, if we imagine that this is the time, and suppose let's imagine that at 20 degrees Celsius, when the temperature is 20 degrees Celsius, the speed of sound is, let's suppose, 344 meter per second. Suppose the sound speed is 344 meter per second. Then when we want to hear the echo, if you are standing here shouting, the sound will go to a place, get struck by that place, and it will return back. So your ears will be able to appreciate the sound only if minimum time taken by the sound to go and again come back, that should be 0.1 second. If the velocity of sound is 344 meter per second, let's calculate how much distance the sound should cover before reaching your ears. So you all know that distance is equals to speed into time. So it's 344 into 0.1, that will make it 34.4 meters. So this sound waves should travel a distance of 34.4 meters before coming to your ears. Then only you will be able to hear that echo. So how much should be the minimum distance between you and that mountain or whatever is that obstruction in the pathway of sound due to which the sound is getting reflected. How much should be the minimum distance? This total distance covered by the sound wave should be 34.4. So the distance between you and the obstruction should be at least 34.4 divided by 2, that will make it 17.2 meters. Why is this 17.2? Because the sound is going to travel towards that mountain for 17.2 meters and again come back for 17.2 meters. So it will take a total distance of 34.4 meters, and then only it will be covering the time as 0.1 second. If the distance is more than this, then also you will be able to hear that echo, and if the distance is less than this, you will not be able to hear that echo properly. You will not be able to make out a difference between the two sounds, and then it will be not called as echo. Okay, so the minimum distance that should be there between the source of sound and the obstruction, if the speed of sound is 344 meter per second, that distance is 17.2 meters. Okay, I hope that is clear to you all. Now, you must have heard sometimes reverberation, but you will say, no, ma'am, I haven't heard reverberation. You have heard it. I know that. I'll make you recognize that where you have heard that. Reverberation during the Diwali, like when it is cleaning going on at home, you must have observed when you clear up all the things from your room, then sometimes you feel that whatever you are saying, that voice is persisting in that room, and the persistence of that sound in the room, that is only known as reverberation. Now, what is this persistence of sound? Persistence means udhar hi rehna. It is there only. So you must have felt आवाज का गूंजना. That आवाज का गूंजना, when you can hear that something voice is like there is some disturbance in the noise, but you can't make out two different sounds. ओके आपको इको सुनाई नहीं देगा, वापस आपकी साउंड सुनाई नहीं दे रही है, बट व्हाट यू आर फीलिंग इज दैट आवाज का गूंजना. So when the room is empty, especially at the time of Diwali, like cleaning, when the cleaning is going on at home, you remove all the curtains and you remove all the things from the room, the sofa, the chair, everything. When you remove all these things, then you can hear that reverberation. So this Diwali, when you clean, when the cleaning is going on in at your home, just try to recognize that reverberation. Okay, so that आवाज का गूंजना, that is reverberation, and when you can hear the sound coming back clearly, that is echo. Okay, reverberation could be there in open space or in closed space. It in both the places could be, but this echo requires at least 7.2 meter distance between the source and the obstruction, so that is possible usually in a open space only. Okay, now one more thing is there, sometimes you hear your sound multiple times. So if you are calling out signs, then multiple times you will hear back signs, signs, signs. So why it is occurring multiple times? Because it is striking many objects. So distance between, for example, if it is striking different mountains, distance between you and one of the mountain is different, and then it is coming from the second mountain also, that distance is different, and it is striking a third mountain also, and that distance from you is also different. So the time at which the different sound waves are getting reflected back, that will be different, and you can hear your own sound multiple times. Okay, apart from that, there is a multiple reflection of sound also. But before that, we need to know that how we can reduce this reverberation. This आवाज का गूंजना or reverberation could be very annoying if you are sitting in a concert hall and you want to listen to a lecture and there is a lot of reverberation. You will not be able to hear the sound properly, and we need to decrease this reverberation. how we can reduce this reverberation? By using fiber board. Means a board is there, so that is made up of fiber that will absorb the sound waves. Apart from that, chairs, table, draperies. What are draperies? It's given in the book now. So what are draperies? Draperies includes thick curtains or thick like some cloth pieces that are usually hung in concert halls so that they can absorb the sound. The seat material of the seats is also selected in such a way that can absorb maximum sound waves, so that can reduce reverberation. All such things like wood, uh, cloth, fabric, they all absorb the sound and reduce the reverberation. Now I would like to add up one thing here that is not there in your NCERT book, that the plants play a very important role in reducing not only air pollution but also noise pollution, because the sound waves are absorbed by the plants as well. So if there are plants around, so whatever the noise pollution is created by the vehicles, so that will be absorbed by the plants. So we all know that plants reduce air pollution, but not only air pollution, they reduce noise pollution also. Okay, that it was something related to sound, so I just told you. Okay, now we have certain uses or applications. Uses or applications means the same only. So uses of multiple reflection of sound. So sound waves gets reflected back after striking any surface, and they don't only get reflected back once, they can get reflected back many times, and there are certain uses of this multiple reflection of sound. One of the use of this multiple reflection of sound is seen in musical instruments. Musical instruments like shehnai, or you have trumpet. Trumpet you must have seen with a bandmaster. No? It's a long tube-like structure, and there's something which we can move to and fro and produce different sounds. Okay. So जब भी बारात में गए होंगे, that time you must have observed a trumpet. So a shehnai, trumpet, they are all based on multiple reflections of sound. They have a typical shape that is having a conical shape, a long tube-like structure is there, and that end of the tube-like structure, it ends into a conical shape. So that when the sound enters into that shape, it gets reflected back multiple times, and after multiple reflections, it comes out and that produce a very nice sound. So this multiple reflection of sound is the basis for the working of musical instruments like shehnai and trumpet. Okay. Apart from that, one more application or one more use of multiple reflection of sound is seen in a stethoscope. You must have seen a stethoscope like this with a doctor. Whenever you have consulted a doctor, doctor must be having, I'll just show it to you. A doctor must be having a stethoscope. This is a stethoscope. So what is there? The stethoscope is used to hear the sound of the heart or the lungs, and that could be heard by the doctor. So this piece is known as diaphragm, that is kept on the chest of the patient, and the doctor can hear the sound coming from that organs through this part. Okay. So this is also an application of multiple reflection of sound. When the sound enters from here and it gets multiple times reflected in this tube-like structure and could be heard by the doctor through this part. Okay, so stethoscope is another application of multiple reflection of sound waves. Right? Next, another use of that is in the concert halls. In the concert halls, when many people are sitting together, just try to observe the next time. In big concert halls, usually the roof is made in a dome shape. Sometimes even a soundboard is placed at the back of the stage. At the back of the stage also soundboard is placed so that it is having this kind of a shape. It is having this shape, and so what happens when the sound is coming from this particular part, it will get struck on this soundboard and after striking it, it will get reflected back, and so the sound will be uniformly distributed to all the people sitting in the concert hall. And for that reason only, we construct the roof as of the concert hall in a dome shape, so that all the sound waves after getting reflected back reach to each and every person sitting in that hall. Okay, so these are the three applications or three uses of multiple reflection of sound. I hope that is clear to you all. All this is important from this chapter. Now, after dealing with the reflection of sound, the next topic that we are going to take up is range of hearing. Okay. Normally, the human ear can hear the sound waves that are having the frequency between 20 hertz to 20,000 hertz, or we can call it as 20 hertz to 20 kilohertz. Why 20 kilohertz? This kilo stands for the thousand. Okay, so 1000 is equals to 1 kilo. So instead of 20,000 hertz, you can write 20 kilohertz also. Both are correct. So the human ear normally can hear the sound waves between the frequency of 20 hertz to 20,000 hertz. And the sound waves that is below this frequency is known as, that is below 20 hertz. Just recall by yourself, that is known as infrasound, also known as infrasonic waves, infrasonic sound waves. And if it is above 20 kilohertz, if it is above 20 kilohertz, then it is known as ultrasound waves. Ultrasound waves or ultrasonic waves. Okay, so the normal range for hearing for a human ear is between 20 hertz to 20 kilohertz. If it is below 20 hertz, that type of sound waves which are below 20 hertz having a frequency less than 20 hertz are known as infrasound waves, and the sound waves that are having the frequency above 20 kilohertz are known as ultrasound waves. Okay, now what happens that it's the normal range just for human beings. In fact, some dogs and the children under 5 years of age can hear the sound waves up to 25 kilohertz. Okay, so up to 25 kilohertz could be perceived by dogs and children under the age of 5 years. Fine. Next, so there are certain animals that can produce and hear the sound waves that are infrasound waves. That includes whale, elephants, you know. So these are certain animals that can produce as well as hear the sound waves that are infrasound waves that are below 20 hertz. So that includes whales, elephants, rhinoceros. They can all hear infrasound waves. In fact, the when an earthquake is about to come, before an earthquake also some infrasound waves are produced, and that could be detected by some of the animals. And you must have observed that is often observed. You haven't observed that, but it's often observed that the animal starts running here and there and they become agitated before an earthquake. This is because of the reason that they can detect those sound waves, and that could lead to earthquake, so they are able to detect those waves. Okay. Next is ultrasound waves. Ultrasound waves includes the sound waves that are having the frequency that is more than 20 kilohertz. 20 kilohertz is ज़्यादा sound frequency होती है, that is known as ultrasound waves. And there are certain animals that can produce as well as detect ultrasound waves. Few examples of that are dolphins. Then we have bats, so dolphins, bats, some moles, some rats. They can produce and hear the ultrasound waves. And one very interesting thing is that bats catch their prey only by using these ultrasound waves. They don't use their eyes for catching their prey. They use these sound waves only to detect their prey and catch their prey. Okay, so the animals that can produce and hear ultrasound waves includes bats, dolphins, then moles are there, some varieties of rats are there. Okay, so that is about the range of hearing. But sometimes you might have seen that people find it difficult to hear even this normal range of voice sound that is produced, but they are unable to hear that, especially in the old age. Then they could be provided with hearing aid. So how does a hearing aid works? You must have seen people that who are not able to hear the sounds, they sometimes use hearing aid, and they put a hearing aid machine in their ears so that they can hear the sound waves normally. How does a hearing aid works? The sound waves are converted into electrical signals by the hearing aid, and these electrical signals are amplified means they are made louder. Okay, so these electrical signals are amplified, and after amplifying they are converted back into sound waves by a speaker. It converts the electrical signals back into sound waves. So what does a hearing aid do? In a hearing aid, the sound waves are converted into electrical signals. These electrical signals are amplified using an amplifier. Amplified means they are made louder. उनकी जो loudness है वो बढ़ा दी जाती है. And then through a speaker, again these electrical signals are converted into sound waves. Okay, so that is how a hearing aid works. Okay. Now the last topic of the chapter, that is ultrasound waves. What are ultrasound waves and what are the various applications of ultrasound waves? So we have seen that if the sound wave is having the frequency more than 20 kilohertz, that is known as ultrasound waves. So now we are going to have to look about the applications of ultrasound waves. Okay, you can remember the applications of ultrasound waves by two ways, by dividing it into two parts. One is the industrial use of it, है ना? In industries or in machinery, how we are using it. And second is the medical use of these ultrasound waves. We are going to talk about both. Okay, so 2 points are there for industrial use and 3 points are there regarding the medical use of ultrasound waves. So first use of ultrasound waves is for cleaning purpose. Suppose we have certain pipes or certain instruments are there that are having a spiral shape, and there is some dirt, dust accumulated in these pipes, and we need to clean them. So they could be cleaned very easily by using ultrasound waves. These ultrasound waves can be propagated in a particular direction, and they will be helpful in removing. They are having very high frequency, and so they are able to remove the dust, grease, whatever particles are there in such of the instruments or such of the things are there which needs to be cleaned, that could be cleaned by using ultrasound waves. So if you have to clean this tube, you can put it in a cleaning solution and then pass ultrasound waves. All the dust and all grease, everything would be removed, and our instrument would be thoroughly cleaned. Very well cleaned. Thoroughly cleaned means very well cleaned and properly cleaned. Then second use of that is when you have to detect if there is any cracks in big metal blocks. Suppose we have a very big metal block and we have to use it for construction of some buildings, or we have a railway track. No, railway track is also a very good example for that. So if we have a railway track and we want to check that is there any crack in this, so we can detect that crack by using ultrasound waves. It's going to be very interesting. Just have a look. So suppose there is a crack here, and a crack in a railway track could be really dangerous. So we want to detect if there is any crack in this metal block. What we can do is we can send some ultrasound waves from here. From one end of the block we are going to send ultrasound waves, and we will be placing some receivers that will receive these ultrasound waves from the other end. So these are the receivers which are going to receive these ultrasound waves from the other end of the metal block. What will be there? These sound waves do not have any interference in their pathway. So these sound waves are going to the receiver. But if there is a crack in between the pathway of some of the ultrasound waves, they will get reflected back. They will not be able to reach up to the receiver, but they will be reflected back. And so by this we can make out, since they are not going to the receiver, that will give, we will get the information that there must be some crack in this metal block at this place. Okay, and that distance could also be calculated by calculating that how much time the sound has taken to come back. By that we can calculate what is the distance of the crack from the starting point. Okay, so this is one of the very good applications of ultrasound waves. Now we come to the medical uses of ultrasound waves. So there are three applications for that. First is echocardiography. Echocardiography means medical uses. First, otherwise it is the third application of ultrasound waves, that is echocardiography. This echo word only suggests that the sound waves is going to strike something and return back. And based on that only, cardio word stands for a heart. Wherever cardio word is there, that represents human heart. So what will be there? The sound waves will be sent and that will get you the images of the heart. So by that you can check the walls are proper or not, whether your heart is working properly or not. So proper imaging of the heart could be obtained on the screen by using this echocardiography, that is utilizing the ultrasound waves. Okay, now remember one thing, this echocardiography is not same as ECG. This is not same as ECG. ECG is something different. In ECG, that is electrocardiogram. Okay, that's not given in this chapter, but I'm just telling you for that for your information. ECG stands for electrocardiogram, in which electrical signals of the heart are recorded. But here we are getting the images of the heart by echocardiography. Okay, you must have some heart ka echo karwana padega. So that stands for echocardiography using ultrasound waves. Now, apart from that, you must have heard about sonography. है ना, sonography करवाना पड़ेगा or ultrasonography. So that is the another medical use of ultrasound waves only, ultrasonography. The principle is the same, but echocardiography is specially used for heart and ultrasonography could be used for any of the body organs. It could be used to visualize your liver, lungs, kidney, or if there are any tumors in the body, or there are any stones in the gallbladder or in the kidney, or to visualize the urinary bladder or the uterus. All these internal organs could be visualized by the technique ultrasonography. Okay, so suppose if this is your kidney and there is some tumor or some stone in the kidney, then what will be there? The density of tissues here is different from rest of the tissues. So the number of sound waves that are reflected back from this area will be different as compared to the rest of the kidney. And so by this technique, we can make out if there are any tumors, if there is some abnormal growth, if there is some stones, that all could be detected by this method. Okay, sonography is also commonly done to visualize a baby. When a baby is growing inside a mother's uterus, the baby could be seen, could be visualized through the ultrasonography. So you can find out before the birth of a child only that if the baby is having certain congenital anomalies or some abnormalities are there. So that all could be detected before the birth of a child only. Okay. Congenital anomalies means at before the birth of a child only the baby is having certain defects. So all that could be visualized by using ultrasonography, which we in common language we all call it as just sonography. Okay. Now, the next application of ultrasound waves is to remove any renal stones. Even renal stones means kidney stones. If there are certain stones in the kidney, that could be removed by ultrasound waves. So these ultrasound waves are projected towards a stone, and that stone is crushed into pieces by using these ultrasound waves. When it is crushed to pieces, now it will be expelled out of the body along with the urine. Okay, isn't it interesting? So by using all these methods, these are all the applications of ultrasound waves. Quickly we'll revise that, we will have a recap. So applications of ultrasound waves, first one we have seen for cleaning purpose. When it's hard to reach places have to be clean, at that place we can use ultrasound waves. Then to detect any cracks or flaws in the metal blocks, that we can use ultrasound waves for that. Then we can use ultrasound for echocardiography, ultrasonography, and removal of any stones from the kidney. Okay, so these are all the applications of ultrasound. So by that we have completed with everything from the sound chapter. Now we are just left with the numerical part, that we are going to discuss the numericals. The first numerical that we are going to practice is from that's given in your NCERT book only, that is after the topic reverberation. So I'm just reading out the question. Try to do every numerical by yourself, but if you get stuck at any of the numericals, you can just go through it and find out whether you have done it correct or not. So the first question is, an echo is heard in 3 seconds. So the time taken by the echo. But before moving on to the numerical, we will just have a basic concept about echo. What is echo? So if this is a source of echo, then the sound travels in the forward direction. When it strikes any obstruction, then it gets reflected back to the person who has produced that sound. Okay, it gets reflected back in the reverse direction. So this is the total distance traveled by the sound. This is like time taken to move forward and plus time taken to move backward. That is the total time. The distance traveled forward and distance in the reverse direction, that is the total distance covered by the sound. So an echo is heard when the sound comes back to the observer, to the speaker. So the question says an echo is heard in 3 seconds. So the time taken for the echo is 3 seconds. What is the distance of the reflecting surface from the source, given that the speed of sound is 342 meter per second? Speed of sound is given to be 342 meter per second. So I hope you remember that you all know that distance is equals to speed into time. This formula we have been using from very junior classes itself. No? Distance is equals to speed into time. So we get a distance 342 multiplied by 3. So it makes 1026 meters. So the total distance covered by the sound is 1026 meters. But are we asked to calculate this distance? No. We are asked to find out how much is the distance between the speaker and the obstruction. So between these, the total distance covered by sound is 1026 meters. So the distance between speaker and obstruction will be half of this, and that is equal to 1026 divided by 2, that makes us 513 meters. So 513 meters, the sound has to go in the forward direction and come back 513 meters. that will make a total distance of 1026. So the answer for the question is 513 meters. If you want to take a screenshot, you can take a screenshot. I'll just shift aside. Now coming on to the questions given at the back of the chapter. At the last, as the exercise questions of NCERT book, question number 7, we are moving to that. A person has a hearing range of 20 Hz to 20,000 Hz, that you all know. What are the typical wavelengths of the sound waves in air corresponding to these two frequencies? Take the speed of sound in air as 344 meter per second. The speed of sound in air is given to be 344 meter per second. You know that the audible frequencies are 20 Hz to 20,000 Hz. And you are asked that what will be the wavelength corresponding to this frequency and what will be the wavelength corresponding to the 2000 Hz frequency. Okay. So before moving on, this is numerical. You should know the formula. So this formula we have studied in the theory part, that speed is equals to wavelength into frequency. But in case you forget this formula, it might happen, you have such a lot of things to remember. So in case you forget this formula, no worry at all, because you all know that speed is equals to, you can derive this formula. Speed is equals to distance per unit time. Everyone remembers that. Speed is equals to distance per unit time. But you know that distance in case of waves is represented by wavelength, that is lambda, and time is the time period of that oscillation. So you all know that frequency is 1 upon time period. That you have to remember. Frequency is inversely proportional to time period. जितना ज़्यादा जल्दी wave, for example this is frequency, तो जितना जल्दी wave move कर रही है, उसको एक wave complete करने में time कम लगेगा. तो time and frequency are inversely proportional to each other. So this time is equal to, upon time, could be written as wavelength multiplied by frequency. Okay. In case you forget this formula, you can derive it at that moment only. If you have some confusion ki kya tha, kya nahi tha, so you can just derive it at that moment only. If you remember that, that's very nice. Well and good. Okay. So just putting the values, we need to find out the wavelength. So wavelength is equals to speed upon frequency. So in the first condition, when the frequency is 20 Hertz, so when we write down, when the frequency is 20 Hertz, then the wavelength is equal to speed, that is given as 344 upon 20, that will come out to be 344 divided by 2 is 172 divided by 10, so it's 17.2 meters. So the wavelength corresponding to 20 Hertz is 17.2 meters, and the wavelength corresponding to frequency when it is 20,000 Hertz, it will be wavelength is equals to speed, that is 344 again, but now we have to divide it by 20,000. So whatever is your answer now, you have to just divide it by 1000 because 20 is common. Okay, so it was 17.2. Now you have to divide this 17.2 divided by 1000. Okay, so 10 will be cancelled out if you move shift the decimal to one place. One decimal will be removed. एक और 0 से decimal will be moving forward. एक और 0 से decimal will be moving even forward. So it comes out to be 0.0172. Okay. You might be wondering, ma'am, why are you telling these things? We know how to divide it by 1000. But in case you have some confusion, any one of you is having some confusion, I'm just trying to help you out. Okay. So divide it by 1000. So shift the decimal to 3 places. Okay. So this is question number, this is the question that we have done. Now you can just take a screenshot. I have shifted to side. The next question. Two children are at opposite ends of aluminium rod. One strikes the end of the rod with a stone. Find the ratio of time taken by the sound wave in air and in aluminium to reach the second strike. Now for this question, in your exam, you will be given the speed of sound in air and the speed of sound in aluminium. Without that, this question is incomplete because you are not expected to remember the speed of sound in air and aluminium. So don't worry at all. If such a question is given in your exams, for any of the materials, you will be given the speed of sound in the two mediums, because without that, you can't find out the answer. So I'm telling you the speed of sound in air, it's actually in your book, it's given at 22 degrees Celsius. It's 246 meter per second. And the speed of sound in aluminium, it's 6420 meter per second. Okay. Now, remember one thing. This question is giving you a very important conclusion. We have read now that the speed of sound is faster in solids as compared to gases. So here you can see the difference. In aluminium, the speed is 6420 meter per second. And in air, it's just 346 meter per second. So you can see how fast the sound is traveling in a solid medium. Okay. Now, before we move on to this numerical, you are asked to find out the ratio of the time taken. But what is the relation between time and speed? We can make it out from the formula also. But remember, no need to find out the formula of everything. Just recall that you all know that अगर कोई object बहुत fast move कर रहा है, तो जल्दी पहुंचेगा, या if it is moving very slowly, then it is going to reach earlier. Obviously, time will be less if the speed is fast. So, speed and time are inversely proportional to each other. अगर speed ज़्यादा है तो कम time लेगा. So, speed and time are inversely proportional to each other. So, we have to find out the time ratio. So, time taken in air upon time taken in aluminium will be reverse of that. Speed of sound in aluminium upon speed of sound in air. You can have to find the ratio, na? So it will be reverse. Speed and time are inversely proportional to each other. So speed, time का ratio जब निकालेंगे, that will be the opposite of ratio of the speed. Okay. Now it's 6420 divided by 342. If you divide it, you will just find out the answer as 18.3. This is the ratio of the time taken by the sound in air as compared to that of aluminium. If you have to find out the ratio, it should be 18.3 ratio 1. Okay. So in aluminium, the sound is traveling 18.3 times more as compared to that in air. You can just take a screenshot if you want. Okay. Now, next question. The frequency of a sound wave is 100 Hertz. How many times does it vibrate in a minute? So in 1 second, it is vibrating 100 times because the frequency is number of vibrations in 1 second. So frequency is given to be 100 Hertz. That means in 1 second, it is vibrating 100 times. Means because frequency is number of vibrations per second. So in 1 second, it is vibrating 100 times. So in 1 minute is equals to how many seconds? 60 seconds. It will vibrate how many times? A very easy question. Just multiply it with 60. So your answer is 6,000 times. Okay. So the number of times it will be vibrating in 1 minute, it will be 6,000 times. Fine. You can take a screenshot if you wish. Next one is really a good question. So the next question says, a stone is dropped from the top of a tower, 500 meter high. So here is a tower, and from 5 meter height, the stone is dropped, okay, into a pond of water at the base of the tower. When is the splash heard at the top? G is given 10 meter per second square, and speed of sound is given 340 meter per second. Speed of sound is given to be 340 meter per second. Small g is 10 meter per second square, and you are asked after how much time you are going to hear the sound of the stone splashing the water. Okay. Before starting to the numerical, just think about it, that what we have to find out. When we will hear the sound of the stone, what are the sequence of events that will be taking place? First, the stone is going to come in the downward direction. Niche aayega. It will strike the water, and when it will strike, after that, the sound is going to come back to the speaker or to the person who is throwing the stone here. Okay. So, हमें क्या calculate करना है? After how much time? It's asked, when is the sound of the splash heard? So, after how much time you are going to hear the sound? कितना time पहले नीचे तक पहुंचने में लगा रहा है? That you have to calculate. The time taken by the stone to reach the water, and then add the time taken by the sound to go in the upward direction. You have to add the 2 times and then you will be getting the answer. Okay. So just find out first. Let us find out the time taken by the sound to reach the ground. Okay. Now you know the distance. You know the value of small g. So how can you calculate t? That will be based on the gravitation chapter somewhere. Okay. So you all know that when something is dropped, are you giving any initial velocity to that? No. So the initial velocity when you're dropping something is 0. So initial velocity is 0. Height is given 500 meters and you are asked to calculate the time. So you all know that S is equals to ut plus half at square. The second equation of motion that you have read in the motion chapter. S is equals to ut plus half at square, or in terms of gravitation we can write H is equals to ut plus half gt square. Okay. Now putting the values, H is given 500. Initial velocity is 0. Anything multiplied by 0 is 0 only. So 0 plus half into 10. Why I'm taking positive? Because it's coming in the downward direction. So it's positive. And t square. T you have to find out. So it gets 5. If you cancel it out, it comes to be t square is equals to 500 upon 5. That is 100. So t comes out to be 10 seconds. So the stone will be taking 10 seconds to reach the water. Okay. The time taken, first you will write that time taken by stone to reach the water. Okay. Please write everything. Okay. So now you have to calculate the time taken by the sound wave to reach back to the speaker. Okay. To the person throwing the stone. So time taken by sound. Next is time taken by sound. Now you all know that speed is equals to distance upon time. So time is equals to distance upon speed. Distance is 500 meters. Speed of sound is given to be 340 meters. If you cancel it, you will find that you're getting the answer as 1.47. Just calculate it and you will get the answer as 1.47 seconds. Okay. So 1.47 seconds time will be taken by the sound. So time taken by stone was 10 seconds. Time taken by sound is 1.47 seconds. So the total time taken, next statement will be total time taken is equals to time taken by the stone plus time taken by sound waves. So that comes out to be 11.47 seconds. Okay. I'll just shift aside so you can take a screenshot. Next question is sound wave travels at a speed of 339 meter per second. So if its wavelength is 1.5 centimeter, you have to convert it in meters. So just convert it then and there only. Don't leave it for later on. So we have to convert it into meters divided by 100. So it comes out to be, when we are dividing by 100, you have to shift the 0 2 places. So 015 meters, that is the wavelength. What is the frequency of the wave? Will it be audible? So what will be the frequency, you are asked? Now you all know that speed is equals to wavelength into frequency. Remember? Remember. And just write it at one corner of this page. Wavelength into frequency. So frequency is equals to speed divided by wavelength. Speed is 339 meter per second divided by 0.015 meters. So I would like to remove the decimal first. So I can write 15 divided by 1, 2, 3 zeros. Okay. Now, denominator of a denominator becomes the numerator. So it will be written as 339 into 1000 upon 15. Remember, denominator of a denominator becomes the numerator. Okay. Now, 3 times is 15. 200 times is this. 3 times is 339. So it comes out to be 22600 hertz. So the frequency comes out to be 22600 hertz. Now it is asked that will this sound wave will be audible to you? No, because audible range of sound is 20 hertz to 20,000 hertz, and it is 22,600 hertz. Okay, so it's more than that. So this sound wave will not be audible. Okay, and this sound wave will be called as which type of wave? Just let me know the answer in the comment section. If you are doing the numericals, if you are practicing the numericals, how many students are practicing that? I'll come to know by your answer. Okay. So just answer me in the comment section that if the sound wave is having this much frequency, that sound wave is called by which type of wave? है ना? That is having a special name that is there. So just let me know the answer in comment section. Don't feel that if one student has given the answer, why should I give the answer? It will just let me know how many of you are practicing that. Okay. So that's all for today. I hope you have completed with all the numericals of the chapter. And if you have doubts in any other numerical from any other book also, if you practice some numerical and you have doubts, I'll be really happy to help you out. You can just post your questions in the comment section. Okay. That's all for today. Good day, everyone. And I'll just shift to side so you can take the screenshot. I hope you have taken the screenshot.